the contents we will follow. We'll have a nice introduction. What is biomaterials and what are the various biomaterials and how magnesium is important, and what are the importance in the orthopedic device. Since I am working in a medical device company, so it is really important, like we can develop the research at the commercial, at the research scale, but taking it to the commercialization is another major step. So it takes a lot of regulatory bodies to, to take research from to the medical device. So that will be the flow of my presentation. So if you have bone fracture, and if you see that globally the bone fracture is increasing tremendously, here you can see a picture of bone fracture, and which is globally increasing like anything, and it could cause due to the sports, it can be due to the accidents, it can be due to various other trauma activities. So how we can fix this bone fracture? So we need to use some biomaterials which will be used to fix this kind of fracture. So with that, we'll develop the implant which will lead to the healing of the bone. If you see the orthopedic biomaterials market or even the orthopedic medical device market, it is increasing tremendously. Like it has a growth rate of 7% CAGR. And if you see the global market, like North America, Europe, Asia, Latin America, Middle East, and Africa, it is literally increasing tremendously. So there is a huge scope for this orthopedic medical device. So if by developing, taking from research to the commercialization, that is a very major step which we need to take care. So if this slide will show that if you see in the orthopedics, the commonly available materials are, people are using titanium, people are using cobalt chromium, and people are using stainless steel. But if you see the properties of these materials, such as density, elastic modulus, or the compressive strength, it is high as compared to the natural bone. You can see it's just 1.8 to 2.1. And if you see the titanium, cobalt chromium, the density is huge. And if you see the elastic modulus, that is very huge. And if you see the compressive strength, that is also very huge. So what does this lead to? This will lead to many problems. And that is why it is the major concern that these are the conventional metallic implants which is available in the market and people are using it. So there was a lot of problems which were dealt with these conventional metallic implants. But on the other hand, if you see magnesium, so if you see the magnesium, their density is very close to bone. It is just near to that. It is 1.8. And if you see the elastic modulus, it is also following the natural bone. If you see the compressive strength, it is literally very near to the natural bone. So I will show what are the major problems which these conventional metallic implants were facing. Due to the mismatch of elastic modulus, which was leading to the stress shielding. What happens during the stress shielding? If you see that due to the mismatch, the implant loosening will happen. Means there are two types of cells. One is osteoblast and one is osteoclast, which forms the natural bone. So osteoblasts are the bone-eating cells and osteoclasts are the bone-forming cells. So which lead to the formation of any bone. So if there is a mismatch in the elastic modulus, it will lead to the stress concentration area to the implant which has been attached to the bone and which will lead to the stress shielding. Due to that strain leading, it will also delaminate the implant from the bone. So these were the major issues with the conventional metallic implants. And further, after healing of the bone, what is the point of having an implant inside the body? So we should come up with a solution that we should use such a material inside the body which will degrade inside the body with the healing of the bone. specifically to the areas where the load bearing areas are less. That is why this idea came into the market, and this idea came into these people of medical device, that we should develop such kind of biomaterials which will degrade inside the body with the healing of bone. And one such biomaterial is magnesium. So why magnesium? If you see the body reactions, you will see that in each part of the body, there's a requirement of magnesium. If you see the brain, a daily allowance of 310 to 420 mg is required. If you see the intestine, there's always a chemical reaction which has magnesium in it. And if you see the other parts, even the bone itself has magnesium ions. Bone is comprises of HA, that is hydroxyapatite, plus collagen. So it's a composite. Bone itself is a composite which has the 65% of HA and 25% of the collagen. And there are other important ions like sodium ions, phosphorus ions, magnesium ions, zinc ions. That is the whole composition of the bone. And there are the growth factors and other things are also involved, like serum and all. But the major point of your discussion is that it has magnesium. But there we cannot use the pure magnesium. Why? Because the standard electrode potential is minus 2.6363 volt, which is very, very high if you compare with standard hydrogen potential, which will lead to the high degradation of magnesium. So that is also not our target, because we don't want the things to be very fast degraded, because if the bone is not healed, then what is the point of having a magnesium? So we should have such material which will degrade with the integration of the bone. What are the various approaches by which we can reduce the degradation behavior of magnesium? We can use alloying, or either we can do the surface modifications by physical or having a coating or something else, or we can make a composite. So the composite will have a better mechanical properties and better degradation resistance as compared to the alloying and surface modifications. So in this slide, we are going to talk about the composite. So if you see here, we try to develop the composites through various two methods. One is through the conventional sintering, and other one through the spark plasma sintering. If you see the conventional sintering, we chose the two composition, one without hydroxyapatite and other with 5% hydroxyapatite. So if I complete the slide, and I will tell you that we have tried to develop the composite by using 3 weight % of zinc and with the hydroxyapatite. Why zinc? Because zinc is a biocompatible material, and only 3% was used because 3% is the limiting solubility of zinc in the magnesium. Beyond 3%, it will lead to the formation of intermetallic compounds, which was not good for us. So another method was used to develop these composites was spark plasma sintering, which is a very advanced technique which is used to develop. Because why this technique was used? Because if you see, it was simultaneously making the composite as well as doing the sintering. So while compressing the green compound and compact, and it was sintering also. These two methods are through the powder metallurgy route. These are the basics of the powder metallurgy route. Conventional sintering is a very traditional, very commonly used, but the spark plasma sintering made the difference, which made the difference in the composite. We could go up to beyond the addition of hydroxyapatite above 5% also. But in conventional sintering, we could only go up to 5%. But when we use the spark plasma sintering, the marvelous results were present, and we could go beyond 10%. We were able to add even 15 and 20. So that was optimized. And we, after 15%, we saw that there was decrease in the properties. So we didn't go above that. So various compositions were prepared, like we prepared 0%, like without HA, then we the increasing 5, 10, 15, and 20. So this was developed through the spark plasma sintering. Now, if you see the bone anatomy, you will see that it is hollow at the center and with increasing layers. So there's a outer layer is known as cortical bone, and the inner layer was known as the cancellous bone. So these are two composition, natural bone which it looks like. So this is how the bone has been developed. So we tried, what we tried, which is mentioned over here, is functionally graded material. What we tried to make the core similar to the cancellous bone, that is using the pure magnesium, and outer layers were changed with the increasing composition of the hydroxyapatite, which we tried to mimic the natural bone, that we wanted a cancellous bone in the center, and with the increasing layers towards the outer part, like the bone should feel that this is my natural part. And because bone is a living tissue, it has its own brain, it can think itself. So the implants which we are using just gives the directional goal, and it just give a direction to grow inward to the bone. But when here, why should I use my strength? So that's why this lead to the stress shielding, which I showed in the previous slide. So here we try to mimic to the natural bone. So this was developed with using the functionally gradient material, making with the magnesium. Then after that, the story is not ended here. We need to check all these properties before going ahead with this material. It should be biocompatible. It should be, the biodegradation properties should match with the healing of the bone. It should have a proper mechanical properties. This is the basic criteria for any implant to be used inside the body, because if it is not biocompatible, there is no point of developing any such implant. Similarly, since the degradation is a major property of magnesium, so you need to check the degradation properties as well, because we need to see whether it is degrading too fast or whether it is degrading on with the healing of bone or not. So further, it should be mechanically stable. Otherwise, there's no point of developing such kind of material. And further, we even checked, like after 3 days or 7 days or 14 days, whether the implant is sustaining such mechanical properties or not. Because if it is degrading too fast, the mechanical properties will tragically drop down. So first target was to develop, to optimize the composition, that how much of percentage of hydroxyapatite we can use in the magnesium. So we took the spark plasma sintering machine and we made these composites with the increasing percentage of hydroxyapatite. And we found out for the 15%, it gives a very nice results. We took the microstructure, and this white portion, if you see, these are the hydroxyapatite, and this in this dark field imaging. And if you see this imaging, these white portions are magnesium, and in this dark field, these portions are hydroxyapatite, which are little agglomeration. If you see, because these are nanoparticles, hydroxyapatite which we are used are nanoparticles, so they have the tendency of agglomerating because of the high surface area. Then we did the mechanical strength, and we found out that it gave the very nice for mechanical strength up for the 15 weight percent of hydroxyapatite, it was approximately 217 MPa, and which was very good news for us. And we try to develop the plate and pin with the help of the composite which we tried to develop over here. And we did the degradation behavior, and they sustained up to 56 days. And we did the longer degradation behavior also, like six months was a full degradation time for this magnesium composite. We checked the biocompatibility. It was found very good. The cells were growing very fast, and it finally we could conclude that magnesium with 15% HA, they have shown a very tremendous properties, and there's a green signal for this that we can go ahead, that magnesium can be used as a medical implant. The next step, mechanical integrity. Now, after checking that this composite is working fine with 15% of HA, now that idea we had in mind, that how much strength has been retained after 3 days or 7 days or 14 days. So this graph which I was talking previously, that this red one, if you see, is the magnesium implant, and the green one, if you see, is the fractured bone. So these two graphs should coincide simultaneously. It should not happen that the magnesium degradation is very fast and the bone has not healed yet. So we need to maintain these two graphs simultaneously. So if you see that after certain period of time, there was complete degradation of the implant. And if you see after certain days, the bone was healed properly, because it takes the bone formation has various steps. Like there's a proper steps which, like, it takes 12 weeks, more than 12 to 24 weeks to completely heal the bone. So there is inflammatory phase. First, the inflammatory phase will come, then the soft callus will form. Then after that, hard callus will form. Further, the remodeling will happen, biomineralization will happen. Then only the bone is completely healed. So there's the main aim to develop any biodegradable implant, that these two graphs should coincide simultaneously. So we made the composite, we took the 3 composition, and we checked for various days, like for day 3, day 7, day 14. And if you see these figures closely, there was a crack development after 3rd day. The magnesium started degrading. And if you see the mechanical strength, it also started dropping down. This was done in 2 different media, because bone, if you see the bone, we try to mimic the environment of the bone. If you see the bone, there are proteins, there are other things involved. So we chose 2 media. One is simulated body fluid, which has all the salts in it, and we chose the other one as modified simulated body fluid, which has proteins inside. We took the fetal bovine serum as the one of the protein which was similar to the bone environment, and we saw the results were better in the case of serum. If you see, the results are much better in the case of modified simulated body fluid as compared to the stimulated body fluid, because it is the most corrosive environment, and the degradation behavior of magnesium takes place in a way that it leads to the development of hydrogen gas. So if you see the degradation equation of magnesium, there is always the evolution of the hydrogen gas. That is the mechanism involved for the degradation of magnesium. So the cracks were also very less in the modified simulated fluid as compared to the simulated body fluid. I mean, this one is the serum and this one is the without serum. So the cracks were fine. So we see that it will not degrade too fast inside the body as compared to the very corrosive environment. So this is, we can say, this is the worst case scenario which we have taken. And there was a drop in the, we calculated the ultimate compressive strength and it was degraded up to 11% for the 15 weight percent HA. And for the pure magnesium, it was approximately 15%. I mean, you can see, you can imagine that how the growth factors and how the serum is affecting the mechanical strength of the magnesium. If there is already the crack in the implant, then there's a chances that it will degrade immediately. But if the implant, so during the manufacturing, we need to take care of lot of things in mind, that during the machining of any implant and the process which we are following, it should not lead to the crack initiated during the implant. The next, after finalizing that, we can use the 15 weight percent HA. So we try to develop the functional gradient materials, magnesium. Why we try to make the functional gradient material? Because if you see that there are a lot of coatings which we can do, but the magnesium melting point is very low. It is 620 degrees Celsius. So the coating was not adhered to the surface of magnesium. And it was not uniform, and it led to the degradation of the coatings, and which was not a helpful feature for us. So we try to develop these through the functional gradient material, and we try to make the concentric with the increasing layers of etching. So to eliminate the drawbacks of coatings, we developed such a system which will have the core of pure magnesium with the increasing layers of hydroxyapatite. So if you see, this initial core is of magnesium with the increasing layers of hydroxyapatite. If you see here in the EDS images, the green color demonstrates the magnesium, and the red color demonstrate the hydroxyapatite. So the red color increasing towards the end. So we can say we successfully developed the concentric functional gradient material system for magnesium through the SPS. And recently, I got the proposal from IIT Kharagpur that they were trying to develop through AI. They were trying to use the artificial intelligence to develop the implant for the functional gradient magnesium material. So I was lucky to review that proposal, and the idea was good, but let's see, they have submitted to some of the funding, so I hope they get it. So this idea they had used through AI. So they are trying to develop the functional gradient materials using the artificial intelligence. And so if I show you the cross-sectional view, if you see that there is a 0% and in the middle, and with the increasing of the hydroxyapatite to the outer layer. So magnesium is the core with the comparable density of the bone, and hydroxyapatite with the interlayers for the structural integrity. And we found out that ultimate compressive strength was approximately 297 for this functional gradient material. This the blue line demands the functional gradient material, and you can see it was like approximately 297, which was better than 15% HA and better than the pure magnesium. So, and we checked the biocompatibility. The cells were very happy. These are the DAPI staining images, and the nuclei were growth on the implant, and the cytocompatibility was fine. This you see is the gene analysis, and the various genes such as ALP, RONX2, Osterix, osteonectin, and osteocalcin, and beta-actin various genes were chosen because these are the genes which are present in the bone, which will demonstrate whether there's even formation of bone or not. So if you see there, when the gel pattern, STS pattern was run, and after day 14, they were white symbols were more as compared to the initial days. So these are the genes which you can see. Were better as compared to the day one. So the RUNX and the ALP, alkaline phosphatase, are the very important genes which needs to be appear during the early stages of bone mineralization. So that is why we were able to confirm that the bone formation was taking place. So we have to take the evidence where, like, even if the cells are growing out, but whether the genes are even helping us to for the bone growth or not. That is why these important genes were taken into consideration, and we run the STS pattern, and we were uh, we were motivated, and we were happy that we got the results which were in line that magnesium can be used for the bone as an implant inside the body. Further, further we now till now we were using the hydroxyapatite, which is already available in the market. So how we can use such a different material that which will help in bone growth faster, because there is lot of problems existing with the hydroxyapatite, because it leads to the agglomeration and the coating was not proper, sometimes bioabsorbable, sometimes cyst formation were taking place inside the body. We got a lot of clinical problems, and we came up with the mind that why not modify the HA, why not incorporate hydroxyapatite with magnesium and zinc while making the hydroxyapatite. So we try to develop modify the hydroxyapatite inside the lab, and you can see that we incorporated it with various magnesium and zinc ions. So we run through some chemical reactions, and these are the transmission electron microscopic images, and we found out there was calcium and phosphorus, but we successfully could incorporate the magnesium and zinc ions. We tried to modify the natural hydroxyapatite, which is already available in the market. So, and we did some XRD analysis, and through using this material, modified HA, which we called as co-precipitated HA, because we co-precipitated the magnesium and zinc ions inside the HA. And through this co-precipitated HA, we tried to develop the various composition of composite through SPS. And again, then we again check all the mechanical properties. So this portion shows the nano indentation studies, and we took the proper indentation in a particular grain, and we found out that the mechanical properties were enhanced with compared to the normal hydroxyapatite, which we were using in the previous slides. So we could say that we can modify the HA with the magnesium and zinc ions, and co-precipitate it and get the good result in terms of mechanical properties. Then we did the protein absorption. This is the major important study. Why? Because when you implant inside the body, the first thing which happens to any implant is that the water gets absorbed on it. So cell material interaction takes place through the absorption of water, and further it leads to the serum or the proteins which are present inside the bone environment gets absorbed on the surface of the implant. The cell material interaction takes place through the protein absorption. So this is the major study which needs to be studied for any implant, because how the cell material interaction even taking place, because if we don't know that, we cannot modify the designs of the implants, we cannot study whether this is even supporting the cells, whether it, because the bone forming cells are osteoblasts, so whether the bone even growing or not. So that's why we studied this protein absorption. And here this analysis, if you see this green color, so we took the various composition, and you can see the maximum it happened for 15% because the CoHA helped in more protein absorption as compared to the without HA and with 5% CoHA. CoHA means co-precipitated hydroxyapatite, which I showed in you the previous slide. So those are the nanoparticles. So, and then we run the general analysis, which was similar to this this image. So we confirm the qualitative analysis and the qualitative analysis. We even done the language absorption model, and we found out that it was matching with the experimental results. So theoretical as well as the experimental results were matched. Then we performed the light dead assay also for this also, whether this is biocompatible or not, how many cells are alive, how many cells are dead. So we did the leaching analysis, and we did the live dead assay that the cells are even happy to be surviving on this implant or not. So that's why we did this assay. And the green color, we are happy to see that cells are really happy on our implant, and we could successfully move ahead with the commercialization, and we can hope for like we get the good results. Similarly, this was the leaching done on the dead cells, and the leach was that more you can see the more cells are there, and in the especially in the 15%. So the co-precipitated HA was helping the implant to develop more cells. Further, we till now all the studies are done in the lab. So, but still we cannot take into the market. There's no point, because we need to do then check the in vivo also. There's no point till the everything goes at the lab level. So we need to conduct in vivo studies. Doing the studies inside the animal is really important. So that is the way we can take any implant to the commercialization. So we did the studies in the avian model. These are the Uttaranchal ultra-fowl birds. Chicken, we can say the Uttarakhand chickens. And we implanted these pins, small pins made of magnesium inside this chicken, and we did the study. So this was the insertion done, and this was the implant, because since the bone is very small for the ultrafowl bird, so we take only very small pin size. And after 24 weeks, what we can see, the bone is fully healed and the implant was completely gone. So this was the happy story for us, that like magnesium can be used inside, and it did not create any inflammatory reactions. There was no, we even checked the serum, we checked the blood, and we did the ICP-MS. So we saw that there was no harmful reactions which was taking place. So we were happy, and we saw that we can use, move ahead. We got the green signal, so we can use these magnesium-based implants inside we can go ahead with the clinical studies. So after that, the two birds were euthanized. So we checked the histopathology, and we saw that the bone was growing fast, and there was no problem in the heart, in the liver, even in the kidney. So the bone growth was was there around this, and it was more in the case of the with 15% of hydroxyapatite. So the composite did well, and with 15% hydroxyapatite, it supported the bone growth. Then we tried to develop this intermedullary pin through the magnesium with 3% zinc, and we inserted this pin in the dog. So what we saw that after 280 days, the fractured leg of the dog was fully healed. What a miracle. So we were now sure that now we can use this magnesium and we can commercialize it and take it to the commercialization. It was fully healed after 280 days. So this is the last slide of my presentation. So what is the takeaway from this presentation? That we can use the magnesium and which is fully degradable, especially in the areas where the low load bearing areas are there, and we can successfully use it, and the bone will be fully healed. What are the future of this magnesium? So previously we were making through the SPS, but now since the technology is moving so fast, the digitalization is happening, so we can use 3D printing, especially now we have the 3D printers. So cells we can accumulate and we can develop the scaffolds, magnesium-based scaffolds, and we can 3D print it and use as scaffolds, especially for the bone defects. So for the acknowledgement, I would like to acknowledge my current company, Oxygen Medical, for giving me the opportunities to develop such kind of materials in the lab. And I would like to acknowledge my previous guide, my Dr. Devupala Lahiri from the IIT Roorkee, for her support. And that's all. Thank you so much. Any questions?
Thank you, ma'am, for such an insightful session. So, participants, if you have any query, you can ask to madam.
Hello, ma'am. Good evening.
Good evening.
Yeah, ma'am. I'm for Anuja from KT University. Actually, as a from patient perspective, I have just only one question. That doctors for the bone problem, doctors are prescribing magnesium, calcium tablets, right?
Yeah.
So for the bone problems, aren't the prescribed tablets sufficient, or we need to go for the composite which you prescribed?
Magnesium tablets which you are mentioning have a separate role. That's why I told magnesium is needed inside the body. So this composite which we have developed, that is for the fracture. If your bone gets fractured, and people use titanium or the stainless steel plates. So instead of using those plates, we can use the magnesium-based plates, which I have showed in the last slide, where inside the dog, we try to insert the magnesium-based intermedullary pin. So that's why magnesium calcium tablets, that is for the daily needs, that your magnesium deficiency is there. That's why they are prescribing the magnesium calcium tablets. But bone fracture, how will you heal it? So those tablets cannot heal the bone fracture.
Okay. Okay, ma'am. Thank you.
Thank you.
Madam, we have one query in the chat box, madam.
Sorry.
We have one query in the chat box.
Okay.
So, R. Venkateswar Rao is asking, in future, magnesium-based alloy may replace the titanium alloy.
Yeah. In the
Is there any
future,
possibility?
yes. There is a possibility that in future, the conventional metallic implants means the titanium alloy can be replaced by the magnesium. Yes. And many companies, there are more than globally, there are more than 4 or 5 companies which are coming with the magnesium. They are even developing the cardiovascular stents. So with the magnesium. So yes, there's a possibility it can fully replace the titanium.
Ma'am, hello. Yeah, since I'm a PhD scholar and I am doing my research on editing in the field of additive manufacturing of titanium alloy. So, as the last point which you told that magnesiums can replace the requirement of titanium alloys. So, only magnesium in form of composites we can use, or we can means magnesium can only form composites, right? They cannot.
No. You can use alloy. You can use the pure magnesium with the surface modification.
Oh, they can be used in additive manufacturing also.
Yes. We can make through additive manufacturing, and you can use the magnesium alloy, which is biocompatible. It depends what is your application. If your application is orthopedics, it should be biocompatible. Then you can definitely replace it with magnesium alloy or yes, composites or surface modifications.
Ma'am, for dental implants?
Dental implants, you can use other such as hydroxyapatite based implants, bioceramic, or you can use zirconia. There are various bioabsorbable implants you can use.
Ma'am, again, because of the cost of titanium as compared to magnesium is preferred, or only due to quality? Magnesium cost is less than titanium?
No, it is not such case. Magnesium, I'm again saying it can be used only in the area with the low loads. You have to use titanium if the high load areas. If you know your leg has tibia and femoral part. So
yes,
the tibia part, if the load area is very high, you cannot use magnesium over there. But in the head, the craniofacial and the maxillofacial areas, you can use magnesium. Or even in the wrist, wrist, hands, where the low load areas are there. There you can use magnesium.
Ma'am, then can we say that the use of magnesium has certain limitations as comparison to titanium alloys?
Yes, because it is fully biodegradable. But if in the hand and wrist, if the fracture is there, what is the point on having a permanent implant? Because revision surgeries will be there. The patient will be affected. He's emotionally and every way it is affected. So why not we use a fully biodegradable system?
Yeah, that means, ma'am, if and only if it is necessary to use for this titanium and this metallic implants, then only we should go for it. Otherwise, we should prefer magnesium and its composites, right?
Yeah.
Oh,
you can say that.
Yeah, ma'am. Thank you.
Yes, dear participant, we are having enough time. You can ask your query to Chika.
Yeah.
Madam Anshu, I have one query.
Sure.
Suppose a patient got a fracture and we have made an implant with a magnesium alloy, and in due course, in the further life of the patient, does this magnesium alloy gets affected by osteoporosis?
Sorry, I did not understand your question. Like you want osteoporosity is caused due to the lack of density in the bone.
Yeah, does the new implant that is made from the magnesium alloy, Will it get influenced by the internal growth of the osteoporosis of the patient?
Yes, if the we can use this. Very good question. So you can use this in the people for the young generation. Like I'm currently working in sports medicine, so this is the area we call it as arthroscopy. So people get ACL tear. If you heard about ligament tear, which is between the femoral and tibia bone. So mostly young generations are the most frequent people and the sports person getting this injury. So we are we are using bioabsorbable screws in that. Similarly, if the person is old and the bone is osteoporotic, so definitely it is not recommendable for that person because the bone growth will be very less.
Yeah, I'll refine my question once again. Mostly, the implants will be used in order to make that bone growth will happen. After that, implants can be absorbable or removable.
Yeah.
In fact, in the case of the magnesium alloy, are we making use of this magnesium alloy based implants in order to make them as absorbable or removable after regrowth of the bone?
No, that's what the concept was. It is fully biodegradable. So it will degrade inside the body with the healing of the bone. So the bone will heal and the implant will degrade.
Can you enlarge your sight on why it is not advisable in older patients? Because most often we can see the patients with fractures will happen with the increase in age, at the same time deficiency of certain vitamins as vitamin D or something.
No, it's not the such case. The bone fracture can happen to any generation of the people, but mostly it happens with the accidents or the sports injuries. These are the common areas where the bone fracture happens. So if you see about the older patients, it is not recommended for them because their bone is already osteoporotic, and so the bone which is already osteoporotic, osteoblast cells will not form faster. So, in the implants which we are using for the bone fracture, the bone should be able to heal faster, which happens in the young generation. That is why in the case of the older patient, mostly if there's a knee problem, we are going for the total knee replacement or the partial knee replacement. In that case, we are using there's a 3 portion of the implant, which is like there's a UHMWP cup and there's a tibia side of the bone and the cobalt chromium. And we are going for the full hip replacement or the partial hip replacement. So that is why in the older patient, the doctors always prefer for the complete replacement of the orthopedic parts, because the bone formation is very, very slow.
Okay. Can this magnesium be adopted as a collagen agent, madam?
Yeah, collagen coating you can do on the magnesium. And currently I'm working on the bioabsorbable screws, which are developed from PLDLA, that is polymer based composite, PLDLA plus silicate ceramic.
Because in the area where knee replacement surgery happens, wherein titanium kneecap and followed by a nylon material, which is a cushioning agent as well as which acts as something like a collagen agent.
No. People are not preferring nylon. People are preferring UHMWP.
Okay. In place of that, can it be adopted titanium magnesium-based alloy as a cushioning agent and can be carried forward?
No, you cannot use biodegradable there because that will be a permanent implant, because there is no requirement for degradation. So it should be yes. If you want, like people have tried like making partial degradable system, like how in the case of stem, which is used in hip replacement, the partial they are making biodegradable porous structure, and the full portion they are developing through titanium.
One last
But there's no authenticated results for that.
What is the human body DNA acceptance of this magnesium alloys? What is the success rate, madam?
Uh, Clinical studies are still going on. We have reached only till in vivo studies. So clinically, cardiovascular stents I have seen. I will share you the article. You can go through it. So they have tested in more than 50 patients. So they told that they are successful in that. And the cardiovascular stent was fully degraded and the heart was fine.
Thank you, madam. Thank you for the answer.
Thank
Any queries?
Ma'am?
Yes, yes.
Yeah.
Sorry,
Please ask
continue.
your query. Yes.
Continue.
No, madam, you please ask your query to.
Yeah, but from the sirs and ma'am's discussion, I just one query is just in my mind, that if earlier we would like ma'am told, it is difficult for the aged people to use this because recovery rate is low, right, ma'am?
Yes, yes.
So if from initial stage, like from the young generation from age 30 on to 50, if we recognize the fracture problem and we replace with this magnesium composite, then will it affect the delaying of osteoporosis or nothing like that?
No, nothing like that. Because for the older patient, if you see we need to, give extra stimulants for the bone growth. And in the child there's a different case, and bone anatomy is little different. In the youngsters, the bone anatomy is different. And in the older patients, their bone anatomy plays a different role. So the surrounding media affects a lot for the bone growth. So fully degradable system and the healing of the bone is the recovery is really, really very slow.
Okay, ma'am. Thank you. Sir, please continue.
Okay. Any other query from participant?
Madam, if any possible research is possibly we wanted to research, what is a possible research area and the topic of this magnesium-based alloys that you can suggest?
Of course, since I'm working in medical device and I'm working in medical implants only, so I will suggest for the orthopedic, or you can go for the cardiovascular stents also. So people are not only limited to these implants, even 2-3 companies, one company from Germany, Syntellex, they have already developed the magnesium-based implants. So people are now going towards the additive manufacturing. So I would recommend that you can change the manufacturing process, or you can use 3D bioprinter with the scaffolds. So you can develop magnesium-based scaffolds or using the spacers.
Okay.
Madam, how this additive manufacturing is being applied in magnesium-based orthopedic implant, madam?
If you want to develop a porous structure, so additive manufacturing will be a area which can help you in developing the porous structure of magnesium. SLS, or you can use stereolithography, various other manufacturing techniques to develop this porous structure.
Okay. SLS can be used, madam, for this
Yes. There's a metallic SLS, so you can use. People are already using for titanium. There are various research available for this.
Okay.
Not the polymer one. Do not use the polymer SLS for developing this. Use only the metallic SLS.
Metal-based.
Yes, okay. Yes. Or laser also you can use.
Okay. Then how do surface modification technique can improve that corrosion control?
Yes. So you need to use the bioceramic coatings on if you want to enhance the corrosion resistance, you need to use, for the orthopedics, you need to use bioceramic coatings, or you can use polymer based coatings on the orthopedic implants or magnesium based implants, which will enhance the bone growth and it will enhance the corrosion resistance. HA coating or the beta TCP coatings or even other coatings are also available.
Okay. So what challenges that will remain when you are balancing the biodegradable and with the mechanical strength, madam, in magnesium? Because
Yes, we face very challenges because that's why we need to optimize what basic alloy we should use. That will the degradation rate should not be very fast. It should be matching. So we need, we need to maintain this mechanical integrity.
okay. So what is the role of, madam, coatings? We can use that coating or any bioactive layer to improve that biocompatibility. What is the role of coating, madam?
The role of coating, it will enhance the bone growth, and further it will help in it will slow down the degradation behavior of magnesium. So we need to use such coatings which will enhance the bone growth. It should support the bone cells.
Okay.
Yes, and it will reduce the degradation behavior, so the corrosion will not be faster, and the bone healing will take place.
Okay, madam. Thank you, madam.
Yes, it will reduce the reaction which happens, that is hydrogen gas is evolved, so it will reduce that reaction, and the hydrogen gas will release slowly, so that will help with even people are using MAO, micro arc oxidation technique, for the magnesium.
Okay.
Yeah.
Any more questions from participants, or else we can wind up the session? Any query from participants? Okay. If not, thank you once again, madam, for your valuable time.
Thank you so much for giving me the opportunity to present.
Yes, madam. So on behalf of our organizing committee and from participants, so we sincere gratitude for your sharing your expertise. In future, we are looking for your other lecture, madam.
Sure, definitely.
Okay, madam.
Thank you.
Okay. So now may I request all the participants can switch on your video so that we can take the snap. Ramnath sir.